This video we are going to discuss complex numbers of class 11. This is an important topic, so watch the video till the end. First we are going to understand what are complex numbers and all the concepts. So if this is understood, you will be able to solve the examples. First of all, consider a symbol I such that I square is equal to -1. Now what does this mean? This means that I is a solution of the equation of the type x square plus 1 equal to 0. A number of the form a plus ib, where a and b are real numbers, is called a complex number. For the complex number, generally denoted by z, is equal to a plus ib, a is called the real part and it is denoted by re of z, and b is called the imaginary part and denoted by im of z. Now for example, if I write a complex number z is equal to 2 plus I into 3, then real part of z is 2 and imaginary part is 3. Two complex numbers, say z1 is equal to a plus ib and z2 is equal to c plus id, are equal only if real parts are equal and imaginary parts are equal. Means a is equal to c and b is equal to d. Like we have real numbers, we have the algebra of complex numbers. First of all, addition of two complex numbers. If z1 is equal to a plus ib and z2 is equal to c plus id are any two complex numbers, then their sum z1 plus z2 is equal to a plus c plus I into b plus d. Means the sum of the real parts plus I into sum of the imaginary part. For example, 2 plus I into 3 plus minus 6 plus I into 5 is 2 minus 6 plus I into 3 plus 5, which is minus 4 plus I into 8. You can write minus 4 plus I into 8 or minus 4 plus 8I. The addition of two complex numbers will satisfy the following properties. Again, as I said, like real numbers, the following properties will be satisfied by complex number. Closure property, if z1 and z2 are two complex numbers, z1 plus z2 is also a complex number. For two complex numbers z1, z2, z1 plus z2 is same as z2 plus z1, and there are three complex numbers, then associative law also holds, which is first you take z1 plus z2 and add z3. It will be same as you take z2 plus z3 and then add z1. Existence of additive identity. There exists the complex number of the form 0 plus I into 0. It is generally denoted by just 0 and it is called the additive identity or the 0 complex number, such that for every other complex number z plus 0 is same as z. Existence of additive inverse. To every complex number z is equal to a plus ib, we have a complex number minus a plus I into minus b, and this is denoted by minus z. It is called the additive inverse or the negative of z, and you can check that z plus minus z will be equal to 0. Difference of two complex numbers. If z1 and z2 are two complex numbers, z1 minus z2 is basically z1 and then you add minus z2 to z1. So 6 plus 3i minus 2 minus I is same as 6 plus 3i and then you add negative of z, that means minus 2 plus I, which is actually 6 minus 2 4 and I into 3 plus 1, which is 4. So it is 4 plus 4i. Similarly, suppose if you do 2 minus I minus 6 plus 3i, so what you are doing is you are adding the negative of 6 plus 3i to 2 minus I. So 2 minus I plus minus 6 minus 3i, which is equal to real part 2 minus 6, which is minus 4, and imaginary part minus 1 minus 3 again, which is minus 4. So ultimately the complex number is minus 4 minus 4i. Now multiplication of two complex numbers. Let z1 is equal to a plus ib and z2 is equal to c plus id. Then their product z1 into z2 is equal to ac minus bd plus I into AD plus BC. Remember this. For example, 3 plus I into 5 into complex number 2 plus I into 6 is equal to AC minus BD means 3 into 2 minus 5 into 6 plus I into AD plus BC means 3 into 6 plus 5 into 2, which is ultimately minus 24 plus I into 28. Now multiplication also satisfies following properties. The closure law, multiplication of two complex number is also complex number. Commutative law for multiplication, Z1 into Z2 is same as Z2 into Z1. Z1 into Z2 into Z3 is same as Z1 into Z2 plus Z3. This is the associative law. Existence of multiplicative identity. There exists the complex number which is denoted by 1, which is equal to 1 plus I into 0, and it is called the multiplicative identity of the complex number Z, such that Z into 1 will give you Z for any complex number Z. Now, like the additive inverse, multiplicative inverse also exists for complex number. For every non-zero complex number Z is equal to a plus ib, we have the complex number a upon a square plus b square plus I into minus b upon a square plus b square. It is denoted by 1 upon z or z inverse, and it is called the multiplicative inverse of z, such that z or z inverse will give you the multiplicative identity which is 1. The distributive law also holds. Z1 into Z2 plus Z3 is Z1 Z2 plus Z1 Z3, and Z1 plus Z2 into Z3 is Z1 Z3 plus Z2 Z3. You need to remember how to find the multiplicative inverse. Now division of two complex numbers. For any two complex numbers Z1 Z2, Z1 upon Z2 is Z1 multiplied by 1 upon Z2. So suppose if Z1 is 6 plus 3i, Z2 is 2 minus I. Z1 upon Z2 is Z1 multiplied by 1 upon Z2 means Z2 inverse. So 6 plus 3i, just now we saw how to find 1 upon Z2. It is a upon a square plus b square plus I into minus b upon a square plus b square. So putting the values and simplifying, we get 6 plus 3i into 2 plus I upon 5. We take out 1 upon 5 common. Then 6 plus 3i is multiplied by 2 plus I. Again, you know the multiplication rule for complex numbers. Z1 into Z2 is basically AC minus BD plus I into AD plus BC. So putting the values and simplifying, you get it as 1 upon 5 into 9 plus 12i. Now how to find the power of I? This is also important. We know I square is minus 1. So now we start from I cube. I cube is I square into I. So minus 1 into I, which is minus I. I raised to 4 will be I square square, that is minus 1 square or 1. I raised to 5 will be, after simplification, I square square into I. That means minus 1 raised to 2 into I. So on simplification you get it as I. Same way I raised to 6 is I square cube of I square, which is minus 1 cube or minus 1. So now, and same way you have I raised to minus 1, I raised to minus 2, minus 3, minus 4. So in general we have a rule. Just remember this rule. It will be very easy to solve the examples. For any integer k, I raised to 4k is always 1. The integer can be positive or negative. That means, say for example, I raised to 4 or I raised to minus 4. That will always be 1. I raised to 4k plus 1 will be I raised to 4k plus 2 will be minus 1, and I raised to 4k plus 3 will be minus I. So by this rule, it will be easy to solve the examples. The square roots of a negative real number. The square roots of minus 1 are I and minus I. Why? Because we know I square is minus 1, and also minus I whole square will also be equal to minus 1. So now symbolically we will always represent root of minus 1 as I. So in general, if a is a positive real number, then root of minus a will be root a into root of minus 1. But root of minus 1 we denote by I. So this is equal to root a into I. So square root of minus a is square root of a into I. For any real numbers a and b, we know that root of ab is root a into root b. When a and b both are positive, when one of them is positive means a greater than 0, b less than 0, or a less than 0, b greater than 0, or if any of a or b is 0. But this will not hold if both a and b are negative. Now the identities which hold for complex numbers, like we have all the identities for square and cube of real numbers, same way the following identities will always hold for the complex numbers. Now two important things which we need to know for solving the examples: the modulus and conjugate of a complex number. Suppose z is equal to a plus ib is a complex number, then the modulus of z is denoted by mod z, the symbol is given, and it is a non-negative real number which is equal to root of a square plus b square. Conjugate of a complex number. If z is equal to a plus ib is a complex number, then the conjugate of z, it is denoted by z bar, and it is the complex number a minus ib. That means if z is a plus ib, z bar is a minus ib. Now from the previous definition, always remember that z dot z bar will give you mod z square. So z dot z bar will be equal to mod z square. And the given identities will always hold for the modulus and conjugate. Now we start with the examples. First example, express the following in terms of a plus ib form. 3 into 7 plus I into 7 plus I into 7 plus I into 7. So now when you simplify this, it is 21 plus 21i plus 7i plus 7i square. But we know I square is minus 1. So it will be 14 plus 28i. So you can write it 14 plus 28i or 14 plus I into 28. Now I raised to minus 39. As we saw previously, the following result always holds for I. Remember that, as I told you. Now since we have over here minus 39 can be written as 4 into minus 10 plus 1. So now it is of the form 4k plus 1, and I raised to 4k plus 1 is always equal to I. So I raised to minus 39 is I, and that is same as 0 plus I. Next example, the given sum you have to express in the form of a plus ib. So first thing is you have to take all the real part common and the imaginary part common. First we have taken the first two brackets and then the third one. So when you combine all the real terms, you get it as 1 upon 3 plus 4 upon 3 plus I into the imaginary 7 upon 3 plus 1 upon 3 minus 1. On simplification, it is 17 upon 3 plus I into 5 upon 3. Fourth one, minus 2 minus 1 upon 3 I whole cube. So first we take out minus 1 cube common. So in bracket it is 2 plus I upon 3 whole cube. Now we have the formula for a plus b whole cube. It is a cube plus b cube plus 3a square b plus 3ab square. So 2 plus I upon 3 whole cube we try to solve with the help of this formula. First of all, minus 1 cube is minus 1. So we take out minus common, and by applying the a plus b whole cube formula, we get minus into bracket 8 plus minus I upon 27 plus 4i minus 2 by 3. Again we combine the real part and the imaginary part. On simplification we get minus 22 by 3 plus I into minus 107 by 27. So you can write this as minus 22 by 3 minus 107 by 27i, or 22 by 3 minus 107 by 27i. Now the fifth sum, again we have to express in the form of a plus ib. In the given example, we use the identity a square minus b square is equal to a minus b into a plus b. So for the numerator it will be 3 square, which is 9, minus I into root 5 whole square, which is 5i square. Similarly in the denominator it is 2 root 2i when you simplify the bracket. Now I square is minus 1. So you have 9 plus 5 upon 2 root 2i. On simplification, it is 14 upon 2 root 2i. Now, since we don't want I in the denominator, we multiply and divide by I. So it is 7i upon root 2 I square. But I square is minus 1. So it is 7i upon minus root 2. Or you can write it as minus of 7 root 2 upon 2i. So the real part is 0 and the imaginary part is minus 7 root 2 upon 2. So the complex number in the form a plus ib is written as 0 plus minus 7 root 2 by 2i. Example 2. Find the multiplicative inverse of each of the complex numbers given below. Now again we will try to first remember the definition of multiplicative inverse. If z is equal to a plus ib, then the multiplicative inverse z inverse is given by a upon a square plus b square plus I into minus b upon a square plus b square. So now for z is equal to root 5 plus 3i. What is a? A is root 5 and b is 3. So now we just try to put the values in the above formula. So after simplification, we get root 5 upon 14 minus I into 3 upon 14. Now we try to understand the complex number with the help of a diagram. The plane having a complex number assigned to each of its points is called a complex plane or the argand plane. In the argand plane, the modulus of the complex number x plus iy, which is equal to root of x square plus y square, is the distance between the point pxy and the origin, which is 0, 0. So suppose you have the complex number, which is of the form x plus iy, then in the plane the point pxy represents it and 0, 0 is the origin. So the distance between origin and p is the modulus of the complex number. Now the points on the x-axis correspond to the complex number of the form a plus I0, means the real part, and the points on the y-axis correspond to the complex number of the form 0 plus I into b, that means the imaginary part. The x-axis and y-axis are called respectively real axis and imaginary axis. Now if you see the representation of a complex number z is equal to x plus iy is given, and its conjugate if you try to represent z bar is equal to x minus iy in the argand plane, then they are the points pxy and qx minus y, and geometrically the point x minus y is nothing but the mirror image of the point xy. Now example 3, we try to do different types of examples based on complex number. If x plus iy is equal to a plus ib upon a minus ib, then prove that x square plus y square is equal to 1. Remember, in all the examples we'll try to use the concepts which we have seen till now. First thing, for simplification we try to multiply by the conjugate. So for simplifying the denominator, so we multiply and divide by a plus ib. So now the numerator is a plus ib whole square, and denominator it is of the form x minus y x plus y, which is x square minus y square. So a minus ib into a plus ib is equal to a square minus ib whole square. But I square is minus 1. So the denominator is a square plus b square. Numerator is a plus ib whole square. So it is a square plus ib square plus 2iab. But again I square is minus 1. So now simplified form will be a square minus b square plus 2iab upon a square plus b square. We take the first two terms and the last term. So a square minus b square upon a square plus b square, and the other term will be 2iab upon a square plus b square. Why do we do this? Because we are taking out the real and the imaginary part. Now this is x plus iy. Now its conjugate x minus iy will be what? A square minus b square upon a square plus b square. Instead of plus it will be minus 2iab upon a square plus b square. Since we want x square plus y square, so x square plus y square is nothing but x plus iy into x minus iy. This is very similar, like we had the denominator clause for the x plus iy which is given. Same way we have over here x square plus y square can be written as x plus iy into x minus iy. Now what you do is you just put the values of x plus iy and the x minus iy which we have obtained. Okay. So now this is equal to a square plus b square whole square upon a square plus b square whole square. On simplification, you will find this is equal to 1. So we have proved that x square plus y square equal to 1. Now example 4. You have to solve the given quadratic equations. Now simple quadratic equations roots were real. We have already seen how to solve them. Similar technique we will use for the quadratic equation in which the roots are complex numbers. So 2x square plus x plus 1. Now what is the formula? The roots are given by minus b plus or minus root delta upon 2a, and delta is b square minus 4ac. You know when delta is negative, the roots will not be real, they will be complex. So here d is equal to b square minus 4ac, which is minus 7. The solutions are minus b plus or minus root delta upon 2a. Putting the values, we get the roots as x is equal to minus 1 plus or minus root 7 into I upon 4. Remember over here, what we have used is root of minus 1 is nothing but I. So for root of minus 7, we have written that as I into root of 7. Example 5. Evaluate I raised to 18 plus 1 upon I raised to 25 whole cube. Now remember, we are going to use the formula which we have seen previously. I told you, please try to remember this. It is very useful. For any k, I raised to 4k is 1, I raised to 4k plus 1 is I raised to 4k plus 2 is minus 1, and I raised to 4k plus 3 is minus I. So now 18 can be written as 4 into 4 plus 2, or it is of the form I raised to 4k plus 2, which is equal to minus 1. Similarly, I raised to 25 is 4 into 6 plus 1, that means 4k plus 1 type. So that is equal to I. So the left hand side is minus 1 plus 1 upon I whole cube. We try to simplify the bracket inside first. So it is minus I plus 1 upon I whole cube. Now what is I cube? I cube is I square into I, but I square is minus 1. So I cube is minus I. So we take out that minus outside. So it is minus of minus 1 plus 1 whole cube upon I. Since we have I in the denominator and we want to get rid of it, we multiply and divide by I. So in the denominator, down in the denominator, it is I square, which is minus 1. Already you have one minus, so minus minus will turn out to be plus. In the numerator, since you have multiplied by I, it is I into bracket minus I plus 1 whole cube. So now what we want to simplify is I into minus I plus 1 or 1 minus I whole cube. Apply the formula of a minus b whole cube. Again on simplification and using the fact that I square is minus 1, we get this equal to I into bracket minus 2I. So it is minus 2I square. Again put I square as minus 1. So it is minus 2I plus 2. So the real part is 2, imaginary part is minus 2. So on simplification, this complex number is equal to 2 minus 2I. Now example 6. If z1 is equal to 2 minus I, z2 is equal to 1 plus I, find the mod of this number z1 plus z2 plus 1 upon z1 minus z2 plus 1. So first we try to simplify the number. We just put the value of z1 and z2 given. So on simplification, it is 4 upon 2 minus 2i. So we have to find mod of 4 upon 2 minus 2i. Taking 2 common, it is mod of 2 upon 1 minus I. Now we try to again simplify the denominator. Since denominator has 1 minus I, we multiply by the conjugate. So multiplying and dividing by 1 plus I, we get 2 into 1 plus I upon down it is 1 minus I into 1 plus I, it is 1 minus I square or 2. Putting I square is equal to minus 1, the denominator is 2. Numerator is 2 into 1 plus I. So ultimately the number on simplification is mod of 1 plus I. Now what is the formula for mod z? If z is equal to a plus ib, mod z is root of a square plus b square. So on simplification, this is root of 1 square plus 1 square or root 2. So the answer to the problem is root 2. Example 7. Find the real numbers x and y if x minus iy into 3 plus 5i is the conjugate of minus 6 minus 24i. So you have to find the numbers x and y if it is given that the first number, which is x minus iy into 3 plus 5i, this is the conjugate of the number minus 6 into minus 24i. So first we try to simplify. Let z is equal to x minus iy into 3 plus I 5i. Now on simplification and putting I square as minus 1 and taking the real and imaginary part different, we get this equal to 3x plus 5y plus I into 5x minus 3y. Now we know that suppose if z is equal to a plus ib is a complex number, its conjugate is a minus ib. So now we are given that the conjugate is minus 6 minus 24i. So now we try to equate the real and imaginary part of both these numbers. Minus 6 minus 24i is minus 6 into minus I into 24. So over here the real part when we equate it is 3x plus 5y, which is equal to minus 6. And the imaginary part, conjugate, is of the form a minus ib. In this form, what is our b? B is 24. So remember, you have to take b as 24. So 5x minus 3y is 24. Now we solve both the equations. You know how to solve the equations. We cross multiply and then try to find the value of the variable. So first we get y is equal to minus 3. When we put y in the given equation, we get x is equal to 3. So the values of x and y are 3 and minus 3 respectively. Next example, again different type of example. If 1 plus I upon 1 minus I whole raised to m is equal to 1, then find the least positive integral value of m. First we try to simplify 1 plus I upon 1 minus I. So again we want to get rid of I from the denominator. So we multiply and divide by 1 plus I. On simplification, the numerator will become 2i and denominator 1 minus I square, which is 2. So we get this equal to I. So now what we have is I raised to m is equal to 1. You want the least positive integer value. Least positive integer value will be 1. So when will I raised to anything be 1? When you have I raised to 4k type, then it will be equal to 1. So for I raised to m equal to 1, the value of m should be equal to 4k for some integer k. Now some assignment examples, please solve them, and in case of any query, please write in the comment section. These examples are based on the type of examples which we have already discussed. So please solve them. First one, solve the given quadratic equation and the answer is root 2 plus or minus I into root 34 upon 2 upon root 3. For any two complex numbers z1 and z2, you have to prove that real part of z1 into z2 is equal to real part of z1, real part of z2 minus imaginary part of z1 into imaginary part of z2. And the hint is you take two complex numbers and then find its multiplication. Find the modulus of 1 plus I upon 1 minus I minus 1 minus I upon 1 plus I, and the answer is 2. Use the formula for modulus. Find the number of non-zero integral solutions of the equation 1 minus I mod of 1 minus I raised to x is equal to 2x. So now this equation is given to us, and when you try to simplify this equation, you will get that 0 is the only integral solution of the given equation. So the number of non-zero integral solutions will be, there will be no such non-zero integral solutions. So the number of non-zero integral solutions will be 0. Hope the concepts of complex numbers are clear. In the next video, we are going to see the questions of complex numbers asked in JEE. So don't miss the video. And for that, please like and share this video and subscribe to the channel.